Good morning everyone. I'm Jeremiah, Product Owner for Team PT Aviation. And welcome back to what I call the trilogy nobody asked for, but everyone's getting anyway. So here we are, Project Task 1. If Assignment 1 was us promising to save aviation and Assignment 2 was us figuring out where to store all the data about saving aviation, then this is us actually designing the blueprints for the life-saving aviation platform. Remember when I said we were monitoring 21 different sensors? Well, turns out that was the easy part. Today we're showing you how we've architected an entire ecosystem of classes, interfaces and relationships that make those sensors actually do something useful. It's like we built a nervous system for a very paranoid, very safety conscious robot that happens to fly planes. What's new since you last suffered through our presentations? Well, we've gone from we should probably track pilot fatigue to here's exactly how we track pilot fatigue using 13 different classes, 7 interfaces and enough UML diagrams to wallpaper Jason's apartment. And yes, Jason actually suggested that. We said no though. The beautiful part, we've managed to create a system where Go, Python and React all work together harmoniously. It's like getting a cat, a dog and a goldfish to perform synchronized swimming. Theoretically impossible, practically improbable, but somehow we made it work. The Go backend thinks it's in charge, Python ML is doing all the actual thinking, and React is just trying to make everything look pretty. Classic tech stack dynamics. Today's presentation is brought to you by caffeine, questionable life choices, and the letter S. For Scrum, which we're still using because apparently we're masochists. Who enjoy daily stand-ups at ungodly hours. Now for moving on. Now you might be thinking, didn't you already choose Scrum in assignment 1? Yes we did, but choosing a methodology and actually surviving it are two very different things. It's like choosing to climb Mount Everest versus actually being halfway up, wondering why you didn't just take up knitting instead. Next slide. Complex architecture management. We said excellent. Reality check. Scrum help us break down 13 classes and 7 interfaces into manageable chunks. Without sprints, we'd probably still be arguing about whether user should be an abstract class or an interface. Small victories. Team size compatibility. 7 people, 3 time zones. Okay, same time zone, but some might as well be in a different dimension with their sleep schedules. Scrum's defined roles actually helped here. Everyone knows their lane, even if occasionally we drift into oncoming traffic. Academic timeline management. This is where Scrum saved us. 1 week sprints perfectly match our submission deadlines. It's like Scrum was designed by someone who understands university project panic. And also procrastination. Multi-service coordination. Go backend, Python ML, React frontend. 3 different languages, 3 different paradigms, 1 shared illusion that they'll work together. Scrum sprint planning forced us to actually define how these services would talk to each other before we started coding. Revolutionary concept, I know. Technology integration. Remember when I said we'd have excellent integration? Well, Docker Compose is carrying that promise on its back like Atlas holding up the world. But Scrum's iterative approach meant we could test integration every sprint instead of having a massive will it blend moment at the end. Now, the product backlog though, that's where things get real. It started as a neat list of features. Now it's a living document that grows faster than my student depth. Every time we complete one task, 3 more appear. It's like coding Hydra, cut off one head, $3 appear. Role clarity has been Scrum's biggest win. As product owner, I translate requirements into something resembling English. Jason, our Scrum Master, keeps us on track and reminds us that it works on my machine isn't a valid deployment strategy. The development team turns our abstract concepts into concrete implementation, usually while questioning their life choices. So yes, Scrum is still our methodology, not because it's perfect, but because it's the only thing standing between us and complete chaos. It's like having a map while lost in the woods. You might still be lost, but at least you're lost with structure. Now giving over to Susan, who will cover the business classes.
Jeremiah. Let's now look at the core business entities for Cogniflight Cloud that are in alignment with our business requirement rules. Users collection is the base entity for all system users, and the pilot, ATC, and sysadmin roles will be based on it. The flights collection will be the core activity unit tracking a pilot's flight sessions. System-generated fatigue warnings will be part of the alerts collection. The edge nodes collection will contain information about the physical device, which is the plane. Telemetry data collected from sensors during flights will be stored in an InfluxDB collection. Further to these, we have domain-specific supporting classes, including Session, which manages user authentication, API Key, which manages edge device authentication, User Image for profile management, and Plane Info and Pilot Info for aircraft metadata and certification tracking respectively. Over to you, Jason.
Thank you, Susan. Now I will be talking about the class design and UML diagrams. So here is the main class diagram. Here we can see the core classes. The user class is the central entity representing system users with basic information such as the object ID, name, email, phone, and password of the user. This uses role-based access control. There is also a profile image and creation timestamp within the user class, which links to pilot-specific information. Next, we have the edge node class, which represents monitoring and control devices with a unique object ID and an associated plane information. The pilot information class shows specialized pilot information, including the certification details and the expiry dates of those certifications, the flight hours and experience metrics, as well as environmental preferences. The key relationships between the classes are as follows. The user-to-session class has a one-to-many relationship. Users can have multiple active sessions. And the user-to-pilot info class is an optional one-to-one class on the user side, because users may optionally be pilots with detail or can optionally be pilots with detailed profiles. The user-to-alert class is a one-to-many relationship. Users both generate pilots and receive alerts. The edge node to flight class is a one-to-many. Edge devices or one edge device can monitor multiple flights. The edge node to plane information classes is a one-to-many relationship. Edge nodes can operate on multiple aircraft. The edge node to API key class is a one-to-one. Each edge node has one set of authentication credentials. Here are the supporting classes. The flight class captures flight operations with the pilot, duration, and timestamps. The alert class has safety and operational alerts with fusion scores and interpretations. The plane information has aircraft specification such as tail numbers, manufacturing details, the model and the year, and the API key class has security credentials for edge node authentication. The pilot environment preferences class has pilot comfort preferences for noise, light, and temperature. Now here's the telemetry data model. So the central class is the telemetry message class, which is the core data container with the timestamp when the data was collected, the stress index, which is a calculated stress level metric, and fusion score, which is a composite score combining multiple data sources. And now we have the telemetry data types. So the heart rate values are cardiovascular monitoring for heart rate, which is the current beats per minute. Heart rate baseline deviation, how far the heart rate is from the normal baseline. RMSSD, which is the heart rate variability metric, which is the root mean square of the successive differences, and the heart rate trend, which is the direction of heart rate changes. Now, the environmental values or the environment values are the ambient conditions, such as the temperature, which is the environmental temperature, the humidity, which basically measures moisture levels, altitude, which measures current elevation and flight altitude. Then there are the eye values, which have eye tracking and fatigue indicators such as average EAR, eye aspect ratio, which measures eye openness, eyes closed, which is a Boolean indicating if eyes are closed or not, closure duration, how long the eyes have been closed for, micro sleep count, which is episodes of brief involuntary sleep, and blinks per minute, which is blink frequency. The motion values are physical movement and orientation, or involve physical movement and orientation, which is X acceleration, Y acceleration, and Z acceleration, which is a three-axis acceleration data. X rotation, Y rotation, and Z rotation, which is once again another three-axis rotation or orientation. And the climb rate, which is the rate of altitude change. The primary purpose of the system is obviously pilot fatigue and stress monitoring, which uses multiple biometric sensors to track pilot physiological state during flight, detect signs of fatigue, microsleep, and stress, monitor environmental conditions that affect performance, and generate composite scores for safety assessment. The telemetry data feeds into the alert system from the main diagram, which triggers warnings when stress levels or fatigue indicators exceed safe thresholds. Now, here are the store interfaces and implementations. Now, for the interface, which is the user store interface, before I get into that, this diagram shows a repository pattern implementation for user data storage using interfaces and dependency injection. Here is what each element represents. So the user store interface defines the contract for user data operations. The getUserByEmail method retrieves users by their email address. The getUserByID method retrieves users by their object ID. The createUser method creates a new user record, and the updateUser method updates existing user information. All methods follow Go convention, returning the user an error for error handling. Now here are the implementations. Here are the implementations. The fake user store uses in-memory implementation for testing. The user's map string user stores users in memory using a map. The create called bool is flagged to track if the create method was called. The create user stores the last created user for testing verification and implements all user store interface methods. The database user store is a database implementation for production. The collection, Mongo collection, is the MongoDB collection reference, which implements all user store interface methods and connects to an actual MongoDB database. Now, the benefits of this design is the following. Testability. We can use the fake user store for unit tests without the database. Flexibility, in which we can switch between different storage implementations. The dependency injections allow for code to depend on the interface and not concrete implementations. And the clean architecture separates business logic from data persistence details. This is a common pattern in Go applications for creating testable, maintainable data access layers. Here we have the session store interface, which defines the contract for session data operations. The create session creates a new user session with the user ID and a role. The delete session removes a session by the session ID. The get session method retrieves session data by that session ID. All methods use Go's context for request handling and return. Session error patterns. Here are the implementations. The fake session store is in-memory implementation for testing the sessions maps.string session, which stores sessions in memories using the session ID as a key. create called bool, which is testing flag to verify the create method and how it was called. The user ID primitive.object ID stores the last user ID used for test verification. The role stores the last role used for test verification. The session ID string stores the last session ID used for test verification. And it implements all session store interface methods. The database session store is the database implementation for production. The collection, mongo.collection, MongoDB collection, is used to reference sessions and implements all session store interface methods and provides persistent data storage. The purpose of this system is that it handles user authentication and session management, which basically creates sessions when users log in, validates active sessions for requests, and cleans up sessions when users log out, and also supports role-based access control. Like the user store pattern, this provides testability with the fake implementation and flexibility to switch storage backends while maintaining the same interface contract. Here we have another repository pattern implementation for API key management. Here's the breakdown. So the API key store interface defines the contract for API key operations. The authenticate methods validates an API key and returns the associated key object. The list keys method retrieves paginated lists of API keys. The get key method gets a specific API key by its object ID. The create key creates a new API key for an edge node, which returns both the key string and API key object, and the delete key method removes an API key by its object ID. All methods use context.context for request handling and follow Go error handling patterns. It is implemented into the fake API key store in memory, which uses in-memory implementation for testing. The keys map primitive object ID API key stores API keys in memory using object ID as the map key, which implements all API key store interface methods and is used for unit testing without database dependencies. The DB API key store database is basically used for database implementation for production. The collection Mongo collection is a MongoDB collection reference for API key storage and implements all API key store interface methods and provides persistent API key storage. The main purpose of the system is that it handles API authentication for edge nodes, which does this by creating API keys for edge computing devices on aircraft, authenticating incoming requests from edge nodes, and managing the lifecycle of API keys, and also supports pagination for key management interfaces. Thank you.
Okay, thank you to Jason for presenting our UML diagrams, for showing off some of the structure that we're already setting up as object-oriented things in especially our backend side on this MongoDB. So I'm going to go more into the physical implementation and the representation of this, and also more into the specific relationships, why they exist and what do they mean. So I'm going to start off with our tech stack and show off, a little bit about our architecture, how these things flow together by explaining it. So here on the next slide, see we've got different tech stack that we're using. We've got all the different versions that we have up here if you want to see and test it out for yourself. The most important aspect of our setup here is the Docker Compose containerization that is used for automatic deployment on the server side. So that Docker Compose can spin up all kinds of containers. It configures all of them. We've got a lot of bash scripting running around to make sure that everything boots up. It's orchestrated so that everything sets up automatically regardless of the state it was in when it got updated. And this means that we can also, and we do this, we have on the GitHub's continuous deployment, we use GitHub Action. Every time that a pull request is merged toward main, we have set up on our cloud server that the thing automatically updates. And now the rest of these are basically containers in our Docker Compose setup. First of all, the most main thing that everything's sort of pushing through and revolving around to get things working is the backend. Now the backend is a REST API written in Go using the Gin framework, and it connects to basically everything. It manages a lot, and it's written in Go because Go is a simple language. It's an easy language to get high concurrency and good performance while keeping things simple. And it also has great test-driven development tools, which I'm going to discuss next when I go to the file structure. So let's imagine this for a moment, right? We have our server, it's set up with VPS, and it automatically deploys this Docker Compose setup, and we have this traffic proxy for our HTTPS. So if you send a normal request to that proxy, it'll just go to the front end. The front end in production is just an Nginx hosting of that folder that is built from the React with Vite, right? So if you just send a normal request to our server, cogniflight.executech.com, then you get that static front end back. If you send it to /API prefix, you get the backend instead. And the backend, obviously that one actually, if you have anything interesting, or okay, let's say better, if you have anything overly intelligent or powerful that can't really be done in Go, then we have merged the bridge with Python. So if you want to do things like generate embeddings for faces, which is used for facial recognition on the edge node, then we put that in the machine learning engine. So the backend, if it's asked to ever generate face embeddings, it'll ask the machine learning engine. We've got RPC working, JSON RPC over an Ubuntu Unix socket. Well, yeah, just Unix socket. And that ML engine is also going to be used to display statistics for our dashboard, and I'll get to that. Let's first talk about our Mosquito. So Mosquito, the actual technology is better than the actual fly. It's a message broker. So anyone that has the rights to connect to that thing can connect to it, and they can publish and subscribe on specific topics. And in our case, the edge nodes are going to connect to the message broker, and it's actually going to authenticate as well. Mosquito is going to connect to my backend and ask, like, are we allowed to use latest user group? Right, we have a plugin set up for that. And once the person is let through, the edge node is let through, then that edge node can start streaming data. It'll stream data about everything that the pilot is doing in that cockpit, how it's going with that pilot, and what it thinks is the fusion score, the fatigue level of that pilot. And that all, what happens is the moment Telegraph boots up, Telegraph subscribes on all the topics to Mosquito, and every single time something comes through, it stores it inside of InfluxDB. So we sort of have an automatic solution for that retention that has already been sort of smoke tested and worked out by many people that have worked with these technologies for longer than we have. And the Telegraph sits there between MQTT and InfluxDB, and it stores things there. And we'll also have a dashboard for InfluxDB. InfluxDB offers a dashboard, so the server will also have a dashboard for InfluxDB available for anyone to log on and see all the data that's retended there, and also access all kinds of different graphs about what the data is doing there in all the different buckets. And of course, while all this is going on, most of the data is being stored in MongoDB, or rather most of the types of data. The Telegraph data might have a greater volume, but it has a lower diversity than the MongoDB data, because the MongoDB data stores almost everything that we've mentioned before: the users, the sessions, the edge nodes, the flights, the pilots, everything. And now on to the next slide. I'm going to show off some of our implementation that we have here. So first thing that I want to point out is look how readable this is. Look how simple it is to notice what's actually going on here. Go is a very readable language. Even if you haven't seen it before, you can see, the user type is a struct, and it's got these fields. These fields have these types, and what happens here is at the right side we also have the serialization information in these backticks. So these backticks are where you can define various tags, and in this case this is for serialization. To say for bsend, which is MongoDB storage, in the bsend version, the ID is going to map to _ID. So when this is stored in the MongoDB document, in the collection in the database, then that's going to reflect the actual schema on that side. And the JSON side, that's going to reflect the same thing. And that is why regardless what happens, when you get something back from the API, you'll find it in this snake case standard, but on the Go side, we actually have it in this capital case standard, because in Go, the casing actually also shows whether that thing is private or public, or in other words, open or internal. Like if it's a lower letter, you can only access it from within the same module. And so everything is capital case in the Go side, snake case on the serialization side. And so yeah, you can see all of our implementations we have so far. This lines up with our UML diagrams from earlier. And as you can see with the user struct, that one also matches with a collection in the database, right? So that one you could actually verify these BSIN fields that they match up with our ERD. And then for the next one, I'm going to show off our file structure. Our file structure, it's already expanding violently. We have a lot of features coming pretty quickly here. And this is a nice commented version that we've got here. You can pause here if you want to sort of ingest this properly. This is a quick description of everything that we have going on. But for this part, I actually thought to show it in the actual terminal. So here you can see I'm on the main branch, right? So let's go to the front end first. So I'm going to make a tree here, ignore the node modules, because the node modules a lot of stuff. And here we have these. This is our file structure right now of the actual implementation of the front end on the main branch. You can see up here we have all of our top level configuration stuff. This is important for anything that is going to inspect the code base or actually deploy the front end for this application. The Docker file describes different kinds of environments. It's used by the Docker Compose that is described a layer up. And the Docker file explains, like in development, that you should just link this thing through with a Docker watcher thing and then run the Vite server. And that's also actually controlled by this Vite config here. And what happens is we actually have a nice dev server set up where if you run this front end on just your local PC and you have the env file set up pointing at our server that's hosted with the VPS there, then this thing will actually reverse proxy to our server. So you don't have to run both the front end and the back end just to test your front end code. And if you descend here into our source code, you can see firstly we have our API. That's the layer that all of the API relevant requests is going to go through on the browser. And this is just a separation of concerns, and it's also going to be very helpful when we have extra security and authentication stuff going on later on, because then that's all isolated to this one place in our folder structure. And you can see this assets here, that's just that's a artifact of Vite that we're going to be using. Anything that we already want to just serve as static components you can throw here, but for our JavaScript components we have JSX files, that's how React works, and we have this components folder for sorting all of those things out. These are all reusable components that you can use for different purposes. And then on our home and login index, this describes sort of the top level structure, and this is where we actually get the structure that comes up if you come into that page. And here we have the sorting of all of our different pages, and you can also here in the main.jsx you have our path description, where we also actually have the React router working, and that thing inspects our URL to decide what to display to the user and what to do in that context. And I'm going to go to show off the backend as well. One thing that you'll notice immediately is that this file structure is a lot more flat. And there's good reason for that, because it simplifies everything here. We don't need nested structures because that also actually messes the thing. But in this case, things being flat actually helps us. And it being this flat, spread out, also helps you to know where to look for something if you want to change something. So we have two different kinds of modules here, right? Every single one of these folders actually matches up with the Go submodule that has its own name that matches with that folder name. So the things like the auth, the edge, image, keys, pilot, these are all groups of API endpoints or middleware. This is code that actually exposes the purposes of our system to the Gen framework so that things work out. And So this is essentially the API part of our actual REST API, but that thing needs some foundation to support it. So we have special case modules that handle those specific stuff. For example, we have a dedicated types module for all of our types that we are managing. And this is where you throw anything while you're planning, while you're working, you throw it here and you access it from the rest of the code base. And then we have something awesome here. We use stores. It should have been evident from what Jason said earlier. We've got these store implementations and interfaces. So if you ever have something that has to be stored, like a user, then it has a user store, a session, then it has a session store. But the stores in the types library aren't actually implementations yet, they're interfaces. So they have to be implemented by something that would actually perform the methods stipulated. And that's actually in our favor, because that means you can have modules like this test util module that can do stuff like implement a user store in the user mark here that doesn't actually store anything in a database but manages it in memory instead. And this allows you to sort of mock up an entire web server during testing, and that way make sure that all these different endpoint handlers and middleware stuff is working properly, and those endpoint handlers and things don't even know that they're working in memory. And this way you can verify automatically. We have it on our GitHub action that whenever you make a pull request, one of the setup checks is that it runs all of the tests on the Go backend, and so you get a marker that says whether this was a good thing or not. And you can also see here on the DB, we've got the flip side. This is where you have the implementation of those interfaces, but from the MongoDB side. So here in DB, this is where you actually implement the stores as MongoDB. And this is what's actually used in production when it has to store the things persistently. And then of course, this main.go, this thing orchestrates everything. The way we've set it up is that these groups of endpoints act as reusable functions. So you can actually, in main.go, you can have the same endpoint just say that can be accessed from here or from there. So in main.go, you'll actually find the definition for the different types of API endpoints as well. And you'll also find the initialization for our MongoDB connection. And you'll also find our bootstrap protocol, which is for if Go connects to the database and it doesn't find any users yet, it automatically creates an admin for you from environment variables that you have provided it so that you can continue. Now, for my next part, I'm going to explain the class relationships. So here we have our interface implementation, as I mentioned earlier with the stores. You have the different interfaces for the different things that have to be stored persistently, but you have two different types of implementing types in all of them. You always have a fake one and you have a DB one. The fake one comes from test util, the DB one comes from DB. And the fake one is stored in memory, the DB one is stored in MongoDB. The fake one exposes testing stuff like whether the endpoint called create while it was being called, or whether, what it made, like what it tried to do with the endpoint. So this mock-up helps us to try and see how is our endpoint behaving under different conditions. Is it validating correctly? Is it working correctly? And this allows us to validate that everything is working properly without booting everything up and maybe messing with the server while someone else is also working on it. And then here we also see embedded types. This is a pattern throughout all of our Go stuff. It's just a power that is available in Go, so we're going to use it. And this is basically like having an instance of one class within another class, except what happens is the fields in that struct get expanded when you're serializing. And the whatever receiver methods is defined for interfaces and stuff actually get inherited as well. So it's a weird trick. It's not really used for the interface part, but it's used to group stuff. This means instead of our telemetry message being one massive 20 field struct, we can label different groups but still have it act as a 20 field struct. And then here we have our association relationships, again reflecting on our MongoDB relationships, showing that a user can have multiple sessions and a user pilots a flight. That's the flight's pilot ID things. And yeah, I mean, this is kind of trivial. You can go through the rest of this. And here we have our aggregation relationships. For example, again, the pilot info is part of the user, and it's also working with the edge node here by key relationship. Yeah. And here we have our different dependency relationships, the different modules that we have here. This is just a demonstration of how, what needs what. And as you'll find, the nice thing that we have going on here is you look at the bottom, most of these things are from the types library. And that's why having a types library makes your life so much simpler, because it's so much harder to have cycling import. Because if you just have a bunch of different random modules that looked relevant, then you could accidentally have them sort of hopping hoops over each other. Okay. And then I'm going to give over to Janku for the non-functional requirements consideration.
Thank you, Brian. Now that we've covered the functional aspects of the system, I'll move on to the non-functional requirements, specifically performance optimization and security. These two areas are critical in an aviation context because they directly affect system reliability and pilot trust. On the performance side, our goal was to ensure that the system can process high-frequency telemetry data in real time without lag. To achieve this, we implemented several techniques. The first is MongoDB compound indexing. By carefully indexing the fields that are queried most often, like pilot IDs and timestamps, we reduced query response times to under 300 milliseconds. That means even under heavy load, data can be retrieved fast enough to support live dashboards and analytics. The second technique is connection pooling. Instead of creating a new database connection for every request, which is slow and resource intensive, we reuse existing connections. This significantly improves throughput when multiple edge devices are sending data at the same time. We also leverage asynchronous processing using Go routines. This allows the backend to handle multiple telemetry streams concurrently without blocking on a single task. For example, while one routine is passing heart rate data, another can be handling cabin pressure or eye tracking metrics in parallel. Third, or final, we applied time series optimization in InfluxDB. By defining retention policies, we can automatically downsample or expire old raw data while keeping aggregated values for long-term analysis. This strikes a balance between storage efficiency and historical insights. Together, these performance strategies ensure that the platform remains scalable, responsible, and capable of handling real-world aviation workloads where delays simply aren't acceptable. Equally important is security. In aviation fatigue detection system, we're dealing with sensitive pilot health and flight data, so protecting it is non-negotiable. Our first layer is authentication, using session ID cookies. This ensures that every request is tied to a verified user identity. On top of that, we apply authorization through role-based access control. This means a pilot, an air traffic controller, and a system administrator each have different permissions, reducing the risk of exposure or misuse. For data protection, all communication is secured with TLS and HTTP encryption. This prevents man-in-the-middle attacks and keeps telemetry secure while it's in transit from the aircraft to the cloud. We also implement bcrypt hashing for password storage. Instead of saving plain text or weak hashed passwords, bcrypt applies strong one-way encryption with salting, making it very difficult for attackers to recover original passwords, even if the database were compromised. Finally, for device-level protection, we used key-based API authentication. Each edge node, essentially each aircraft device, must authenticate with a unique key before it can send data. This ensures that only trusted sources can feed into the fatigue detection system. So in summary, our non-functional design balances two priorities: performance, so the system can perform vast amounts of sensor data in real time, and security, so sensitive aviation and health data remain protected. Both of these elements are critical in making sure the Cogniflight Cloud platform is not only functional, but also robust and trustworthy for real-world use. I'll then hand over to Jeremy for the encapsulation and data hiding.
Good day, ladies and gentlemen. My name is Jeremy, and in this portion of the presentation will be focusing on encapsulation and data hiding. Let us begin. Within this slide, we pretty much have access modifiers. We make use of three types of access modifiers as well as the Go convention and their usage. Starting off with the public access modifier, in which we use capitalized names for the methods, and we'll be implementing this within our API external usage. Next up, we have the private access modifier, in which we use the lowercase names for internal implementation details. This will cause us to hide these particular data from everything outside of the own package. And finally, we have our package access modifier, in which the types and functions within these internal packages are only then accessible to other codes within the same module. And as a result of this, it will enforce strong model boundaries. Next up, we have the interface segregation. As you can see from the code snippet there are two interfaces declared, user store and edge node store, alongside the respective methods within each one. Within the user store, we have the get user by email, get user by ID, and etc., as well as the get node by ID and the create edge node methods within the edge node store. These methods are then declared within these interfaces because these methods will be used by a certain portion of the system in order to make something function. That's very important. And as a result, this will then help us to minimize dependencies, ensure that the testing is easier, and ensure that you can swap implementations without breaking certain aspects of the other code. And yeah, that's pretty much it. You want to create a system that's robust and secure, that will be able to protect the data that we will be storing from unethical hacks or attacks in that instance. And yeah, that's pretty much all. I'm just going to be passing over this portion of the presentation to Jaden. Thank you.
Hi everyone, my name is Jaden Crossan. I'm going to be doing the validation and business rules for this part of the project. So first up, here you can see the validation matrix. Each entity has fields with specific validation rules and error handling. For example, for users Go field, we use RFC 5322 regex, and if validation fails, we return a 400 bad request. React with Vite uses enum validation, defaulting to pilot if no match is found. For pilot infill, we apply a format check while MongoDB alerts and clamps within the billet range from 0 to 1. Finally, flight values in InfluxDB must always be positive, with negatives being rejected. If we move on to slide 8.2, here's an example of our business logic for generating alerts. If the telemetry fusion score is greater than 0.7, we trigger an alert. The alert captures the pilot ID, the current timestamp, the fusion score, and an interpretation of that score. Finally, the alert is created and stored. If the score is below the threshold, no alert is generated. Thank you all so much. That was my part of this project.
Alright, thank you Jaden. Let's bring this bird in for landing. Let's talk about what we've really accomplished. First, we created a business class architecture that makes sense even at 3 AM when you're running on energy drinks and desperation. 13 core classes from users to telemetry data, all working together like a well-oiled machine. Well, more like a machine that occasionally needs percussive maintenance, but it works. Second, our UML diagrams. We've got class diagrams that would make a computer science textbook jealous. Inheritance, aggregation, composition. We used every relationship type except it's complicated. Though honestly, that describes most of our code relationships accurately. Third, the interface implementation. We created separate interfaces for everything, because apparently we hate ourselves and love abstract concepts. User store, session store, edge node store, we've got more stores than a shopping mall. But hey, it's solid principles in action. But here's what actually matters. We've designed a system that could genuinely save lives. When a pilot's fusion score hits 0.7, our system doesn't just notice. It screams bloody murder to everyone who needs to know. That's not over-engineering, that's engineering with purpose. So there you have it. Cogniflight Cloud's class and UML architecture. This team has taken abstract requirements like monitor pilot fatigue and turned them into concrete implementation with actual code, actual structure, and actual hope of working. We've normalized it where it makes sense, denormalized it where it doesn't, and created interfaces for everything, because apparently that's what good developers do. Our encapsulation is tighter than airport security. Our validation rules are stricter than my mom's curfew rules, and our business logic is more complex than explaining to non-tech people what we actually do. Remember, In aviation, as in software development, it's better to be on the ground wishing you were in the air than in the air wishing you were on the ground. Our code follows the same principle. Better to have too many safety checks than to have planes going, doing unexpected lawn dart impressions. You don't want that. And that's it. Thank you for watching and have a lucky day.